In this video, we're going to discover one of the most important ideas that you'll ever learn in all of computer science. That is the binary search tree. This is such an incredibly famous and important data structure that I can virtually guarantee it will come up in your life if you go to a job interview or talk to basically anybody ever about anything in any circumstance. Maybe I'm exaggerating a little, but binary search trees, they're kind of a big deal. Now, it's no fun if I just tell you what they are, so I'm going to force us to actually invent them together. And I'm going to start by analyzing a kind of funny way to implement a set. So imagine that we have an implementation of a set called ordered linked list set. What is it? Well, it's a linked list where all of the items are in order. So if I have the set of the letters A, B, C, D, E, F, G, we have a sentinel node that points at A, which points at B, which points at C, all the way up to G. And we also have a size variable that makes it easier for us to calculate the size. So what I'd like you to do now is identify one of these operations that will be slow, that is linear time, theta n. Okay, so turns out contains and add will both be linear time. If I want to see if the set contains G, well, I go to the sentinel, I hop forward, and get to G. Not so great. So the problem here is that even though our linked list set is in order, we're not taking advantage of that fact in any way. But it feels like maybe if it is in order, there's something we could maybe do. So there's actually a lot of approaches to taking a linked list set and making it better. Sorry, an ordered linked list set and making it better. And just to give you a sense of a slightly more exotic approach than the one we'll get to in a moment, we could add random extra links. So one optimization is I'll say, well, A, you have some extra links. Maybe A goes to D, and B has an extra link to G, and you can have maybe 5 links coming out of A to various points in the list. And that's actually a real data structure known as a skip list, and it relies on randomness to get very good performance. And that's not going to be the idea we discussed today, but it is kind of cool that you can take an ordered linked list, add some express lengths, and actually get, and we won't prove it or even discuss it in any detail, but you can get expected logarithmic time on your operations. And if you want to learn more about that, you can click this link. But no, what we're going to do now is we're going to invent, as I promised, the binary search tree. So the first thing I'm going to do is I'm going to move the pointer to the middle of the array, of the linked list. And what I mean here is that instead of the sentinel node pointing at A, we're going to point it at D. Now we have a problem here, which is that we can't get to the items on the left, so we'll just turn those links around. And now what we've done is we've actually halved our search time on average. So if I want to find an item, like say G, instead of having to go through the entire list, we start at D, and at this point, we know which way to go. Because it is in order, we know that G is going to be off to the right, because G is greater than D. So we'll run off to G, and we get the answer in half the time. So now what I'd like you to do is figure out, how do you do even better? How do I get to a fully optimized and just the perfect and most beautiful structure that's going to take advantage of order? So just think about what that might be. Pause the video and try it out. All right, so it turns out we can do basically a recursive version of what we did before. Because D, we can think of it as, it's a starting point. And now what we'd like to do is point to the middle of what's on the left and to the middle of what's on the right. In other words, we'll take the pointer that's coming straight out of D and point it at B, and the right pointer and point it at F. And that will give us, after we turn these links around, a new, nicer structure. And there, lo, behold, the binary search tree. So that's pretty nice. What we have now is a data structure which will allow us to find anything in only 2 hops. And as we'll see, going from 7 to 3 to 2 is pretty cool. But we'll see that there's an amazingly huge asymptotic improvement when it comes to search. So that's the basic idea of the binary search tree. So in the next couple of videos, we'll explore this in a little more detail. That's it. We invented it. Good job.